sleep. It's a bit after midnight, and I'm going to stay up late tonight and see if I can finish making this language. This is something you should be able to do in a sitting, right? Like you don't have little children yelling at you when your pharo instance isn't crashing. Let's see. So if you were watching the previous one, there was a incident where I made I had an error that was causing. Second here, I'm going to turn this off. Stream is live. Making sure that it's running. Okay. I crashed this thing twice, and it looks like what happens is when I came back and ran it in the debugger, because I didn't want to like start the stream off with a just absolute crash again. When I run it in the debugger, what happens is make this panel, step into that, step over basic new, and then step into the initialize. And basically, everything works fine right up until I start adding the child. So I create this vertical pane, and I make some buttons, and I make a stack frame. Everything's fine. And then I add those children to the vertical pane. Everything's fine. And now I'm going to add this child to the work area. And as soon as I hit that, it's going to lock up and just completely freeze. So I think the issue is that the work area by default, okay, so I might be completely frozen here. Hope I caught it in time. Okay. I have to kill it. I did this a couple times a moment ago, and I didn't have to kill it then, but I have to kill it. He looked at the debugger with murder in his eyes. Okay, so I'm killed. Yeah, we're up to like 5 gigabytes here. I'm gonna just kill it before it gets out of hand. I don't want it to crash my machine because it was like blocking up OBS and everything before the broadcasting software. So let's fire that back up again. I have saved everything at the end of that. I made sure to save the state. I just need to bring up, and if I click here, I definitely will crash for sure. But it's actually the debugger, so it's the Vex debugger panel that I need. And when you look at initialize, it's adding this vertical pane to the work area, causing the trouble. And the work area is defined here. I have this tendency to, 1 second, let me turn on my light here. I have a tendency to name things that create a visual component on the screen. I've kind of following this convention where I call it make something. So this defines a property called buttons. This defines a thing called stack frame. And so make work area is the thing that defines the work area. And just here it's a horizontal flow. And I think what I want to do is instead make this a, I just want to just rewrite the work area. So I'm going to put this here and just redefine that in Vex debugger panel. And I'm just going to make that the BR vertical pane that I want directly. So BR vertical pane new, and match the parent so that it expands to fill up all the space. And then we can follow all that exactly. Then add children, and then we will add the self make buttons and self make stack frame, which I'm not sure is the right word for that. There we go. Save that there. Then this can just be reduced to just changing the title. And I think we should be good to go now. Just in case, I'm going to save this here. I'm going to save the state of the system in case this crashes again. but I'm not expecting it to. I think that was the issue. I think it was just some kind of issue with sticking a horizontal, like a vertical thing with a horizontal. I was just nesting too many. Like, I think this is an issue in Brick, the library that does the GUI layouts, the layouts there. So I'm using a library called Block, and then on top of that is Brick, and then on top of that is Glamorous, and the whole this gray and white UI is the Glamorous toolkit. That's called Glamorous toolkit. Go to gtoolkit.com. It's a novel interface for pharo for Smalltalk. You don't have the little windows everywhere. Tab based, and it's got a nice. It's called Flow. PHOW. I really like it. I really like this environment. It's kind of become my go-to environment for like building anything. But and I've been building this animation tool inside of it, and yeah. Anyway, hopefully, I'm thinking this is probably going to stand alone even without that. So let's now that we've saved this state, let me just do a sanity check here. So initialize makes the work area. The work area makes the buttons in the stack frame, and these are just pieces of text. And so that should all work. And then once it connects to the RPN, this is what I was trying to do as I was done. So the RPN builder is the interpreter basically that I'm building. And it's got a list of tokens that it's going to be stepping through. The interpreter is just interpreting a list of symbols. And each symbol is either going to be a method call on that object or something that we've defined within the language. And so the intent is that the buttons would actually be real buttons. Right now, it's just going to be the word step. And it would be like a little debugger. And the stack frame is going to be, again, that's not the right word. It's really like the list of instructions in the current thing that you're running. So either a definition or the top level thing that you're running. So, and together that makes a debugger. So I'm expecting that to happen. And as soon as you send the text to the debugger, it tokenizes it, rather to the interpreter, it tokenizes it, and then it should update on the screen, and then you should be able to step through it. That's the plan. We can't do it now because we don't have a step button, but I think we're very close to having it. Okay, so let's check this and see, cross our fingers and hope that it works. It didn't work. Okay. And we're up to 5 megabytes again, or 5 gigabytes again. What the heck? This is not, I'm debugging GUI stuff. Like, why am I, that's crazy. Did I not save those changes? Okay, let's just make sure we can make one of these. The changes are there. Okay, so if we say we say Bex debugger panel new, and we just hit Control G. Why? Why is that crashing? This is a bug in Glamorous. This has nothing to do with me. Either I'm doing this wrong. All right. I mean, I'm going to get rid of that horizontal flow. I think that is something I introduced. I had these things. It's just 2 strings. I had 2 strings on the screen. BL text element new, BL text element new. So I'm going to get rid of this one and just make the stack frame be this. Let's try that. As rope text. Okay. Oh! I'm not returning these things. So it's returning the debugger panel. Yeah, that's an infinite loop. Okay, that's me. All me. if you don't use this return, then by default it returns the current thing, and so it's putting a debugger panel inside of a debugger panel inside of a debugger panel, and yeah, infinite loop. Okay, it is me, my fault. I shouldn't be so quick to blame the tools, but this tool is not. It isn't a 1.0. It has reached its 1.0 thing, but that's just kind of a number. You know, it's still a new framework, and it does tend to occasionally break on me. Sometimes it's my fault, sometimes it's their fault. So, okay, so this should work now. This I would expect to work. Oh, I lost a little thing. Actually, in this context, self is just the best. I can even just say self new. Hit Control G now. Okay. That's what I expect to see. Be able to, no, you can't drag this. Okay. Okay, it's throwing errors as I. This is also a common thing. You can't. Okay, I'm going to close this whole window. This is working. Everything's fine. This is another failure mode of Smalltalk. If I can make a new window pop up, like if I just not have the mouse over here, like I don't have to kill this, but I'm going to. Okay, this way, because I've got like 8 million debugger windows open. As soon as you get a mouse error, then you drag your mouse, and every one of those events triggers an error. You get 100 errors. Okay. But this is fixed now, so we're good. We're good. Okay. Why did that? Okay, just why did that happen? Because I tried to drag the thing that popped up, and it just wasn't. It was saying error message about GS left. Oh, because it's looking for a dock. It's looking to see if it's close to the dock or not, and there isn't a dock. So you're supposed to only have this inside of a container, and I don't check for that. Okay, so this is good. So let me just make sure that I've changed that. No, I didn't save the changes. So I think this is actually fine, even if with the BL horizontal flow, so I will leave that there. And because I want it to be a horizontal flow, because I'm going to add all the tokens, and then the tokens will. Everything named make now has a return area. This was probably fine. I probably didn't need to do this step, but it's okay because I can just make it a BL. That's actually exactly what I want anyway. All right, so once again, I'm going to save this, but I do think it is fine. And now let's get back to writing some writing a language. Little time to save. As long as we're not taking up gigabytes of RAM or everything. It does have to. I believe what that does is it walks through like. I mean, it's saving everything in memory, so it's like saving. I don't really know. Like the virtual machine ought to just be able to dump all the RAM to disk. So I don't know what else it does. Anyway, I expect this to work now. Yes, there we go. Okay. I see this says stack trace, so somewhere I'm missing the stack tra. Somewhere I'm missing a call to match parent. So this is going to be a thing. So this is BR horizontal flow. Actually, it's a horizontal pane. New. I'm not sure what the difference is. I think the flow wraps. I have never really verified that. And then we're going to add child. Put it in parens. We're going to even make it background, and just give it a color, color very, very light. And we'll add this child. That'll be like the first button. This is like a stand-in for the first button. And then this, so this would probably be, we want to say horizontally match the parent and v exact 20 pixels, 20 points. I think it's actually points, which are like twice half a pixel. I'm not sure. That might be too small. But I might be confusing myself as well. Okay, so and then the stack frame part is going to be match parent. So we're going to fill up the rest of the space. And I'm not going to worry about trying to save that now. And next time I open this, I expect this to be like light gray and all the way across, and then this would be inside. Should say the word stack trace. Close that. Boom. There we go. Stack frame. Oh, and I put padding in there. I think I should probably change that. I actually did put padding in here because it says BL insets all 2. And I think I should put that on these two things. Both of these should have padding, but not the thing as a whole, because you don't want white shiny through. This has nothing to do with making a language. This is just visual design. Right. Little glimpse into the GUI framework I'm using. There, that's perfect. That's how I want it. And these would be buttons. And that is a reasonable height, or I guess it's matching the content. Probably I should say fit content rather than be exact. Exactly what to fit be exact, I should say V, so vertical fit content. Okay. And just perfect. Okay. So now the stack frame is going to change to one little box for each token as soon as I press this button. That's the hope. There we go. And now we're going to step through them. So and then I guess self redraw stack frame. So okay, so what happened here? If you didn't catch the last bit, or basically this takes this string, breaks it into a bunch of tokens on breaks on spaces on any white space, gives you the words, and then those words are stuck into a buffer, and then it emits a thing called stack frame changed. It issues this command, right? This event, that stack frame changed event. So now I need to make another event for when the IP address changes. The instruction pointer. the IP for instruction pointer. And so that would be a new event, a new announcement, called X I instruction pointer change, instruction pointer changed event, and the superclass is announcement, and let's put the new IP address in. Okay. And maybe we'll give it start putting this in called events. Probably we have the other one. Oh, maybe it should go in RPN. I don't have a strong preference here. Change that to RPN. These have no, again, no particular meaning to them. They have no they don't change the semantics of your program. It's just an organizing tool. I have no comments anymore. This is really the interpreter, right? So, should I rename this? RPN. Really, RPN interpreter. I think so. It is both a builder and an interpreter. It builds the image, but I'm turning it into an interpreter. Interpreter for a small stack-based language that builds diagrams for Boolean expressions. Okay. Now when I click on it, at least have one comment. Okay, so this thing is going to well, we need a step event, right? So this is the interpret the current token. And we're going to expand this logic a little bit, but we also need a step event. So let's just create a method called step. So the kernel of pharo has stepping built into it. We're not going to worry about that. That has something to do with like the old school graphical user interface called morphic. Anything could be like a visual object in the whole thing. Very cool, but got kind of messy over the years. All right, so step, we're going to so we start at 0. Instruction pointer is currently at 0, but everything in Smalltalk is 1 based. So the array started slot. The first slot in an array is slot number 1. So this actually works out kind of nice because we can say IP is equal to IP plus 1, and then if there's no if in Smalltalk, then this value. So now IP greater than current token. So what is current token? Save this. Save this. And let's look at what current tokens is. I think it's just tokes. Yeah, so tokes. So if so IP greater than tokes size, if that's true, come here. If true, then what will we do? We return, which does what? All right, so we'll say self-return. Otherwise, if false, self do token tokes, and then you say tokes at IP. Not going to work because we need to send an event as well. We need to do this we probably want to do this at the end because we want to show the thing that we're about to run. We want the IP address to be, or I keep calling the IP address, the instruction pointer to be pointing at the thing we're about to run, not at the thing we're currently running. Because every time we step, we're going to execute the current thing. Yeah, this is right. This is how I want it to be. Okay. And then IP equals IP plus 1. And so then we say so we say announcer announce vex announce colon vex instruction pointer changed event new, and then we have to tell it what the IP is, and then the IP. So save this, and then we will actually add this to vex instruction pointer changed events, and we would just say a number, the IP equals a number. I did add it as a slot already when I created the class. Okay, so that's saved. And then return is going to be we'll go ahead and create it, and it's part of the execution stack. Okay, I'm just going to save it here. So let's look at what return does. So we're returning from a function. So we need to let's browse here. So if you look at the execution stuff. So when we first start out, the control stack is empty. And then when we run this reset thing, really the control stack should be empty here too. And the data stack should be the data stack. So data is the other stack. So we have two stacks and a dictionary. And the dictionary is going to stay persistent. So the dictionary is a list of, or rather, it's a dictionary that maps names of words, like words, to a list of tokens that are just the symbols that representing those words. And so that's how that it's just like almost like an assembly language, like one word after another, and each word is just immediately executed, unless it's one of these defined words, right? Right. So the definitions, you keep adding the definitions, and then at the top level, you can just reset everything and keep the definition intact, and then tell it to do some new thing. This is what we want, and then in the initialization, actually, we can actually change this to just call reset, and then this gets set away. So really we can, and yeah, so this should be here, this should be here. This is the dictionary new. So make ourselves visible to the graph, to, I'll just give it a name, to X debugger panel. The base shows the actual data structures. Right. We will probably replace this. Probably we usually we replace this. Or rather, it's not usually, but you know, if you run it like just as a Bex RPN interpreter, you just get like data structures. There's no drawing. So Bex sketch app replaces this with a Bex scene base, which is a wrapper for Bex base that takes those data structures and also builds the diagrams. And then the rest is our Fortlight interpreter, and then that's defs and self reset, which does all this stuff. There's mud. Okay. IP address is 1. IP address. It's not an IP address. I don't. Instruction pointer. IP is 1. Okay. So now we're going to have two things: call and return. But actually, this is okay. We don't have. There are no definitions yet. So since there are no definitions yet, we can. These are all primitives, and we can just run through them. And so what I want to do is I think I'm going to give this an IP address as well. I mean, an instruction pointer as well. So I'm going to say IP. I'm just going to call it the IP. I mean, it is an address. It is an IP address. It is the instruction pointer address. It is an address in the it's an address in the list of it's an index into the list of tokens actually that we are currently executing. Okay. So anyway, the IP is going to be. We could even leave it there. And then I will add this as well to that other. Which makes me think there should be some common thing called a number. IP is a number that is called like a Vex interpreter event or Vex interpreter event or something. Okay, right now we just have two of them, so we'll just. Okay. Because you'll get so the idea is that like if you're here on this event and then you step into it, then when you step back out, we want to get an event and then we want to restore all the tokens and then highlight the next one. So that's the idea here. Probably we should also show the stack. So probably missing a little bit in this thing. Maybe we should whatever. Maybe I'll have the stack on the left as a vertical thing, and then the list of tokens just as a vertical thing, and put a scroll bar. We'll see. Okay. Yeah, I've never done. Normally when I write this, I don't break it out into a debugger where I don't start with the debugger. I don't know if I've ever made a debugger like this. I've made it inside of like RetroForth. I guess I've made debuggers like this, but yeah. All right, so what am I doing? I want to update this drawing by having the instruction pointer, the current token highlighted, basically. So I need to load up that debugger. So Vex debug panel, debugger panel. When we redraw the stack frame, let's keep an IP address here as well. Address IP current is like token index, so IP is the current thing, and we're going to initialize that to 1. It doesn't really matter. We're going to override this every time we get an event. And so when we reset this, self redraw stack frame, so we're going to get the event. I am going to go ahead and make, because now I need a accessor for both of these. So I'm going to make a new class called just Bex interpreter event. Superclass is going to be an announcement, and then the slot is going to be IP. And we're going to do this. And then, so the instruction pointer changed event. We have to remove this slot, I think, to make it. Remove the slot. And then we can make the superclass be Bex interpreter event. And then we can move this up. Right click here and we say push up. It's not there. Push up method. I don't know what the logic is about how you do this, but the push up method, like why that appears sometimes it doesn't. All right, so now we should have IP, and then we should have another one called accessing. Always called accessing. And then IP is just going to return the IP. The IP. It's just going to be an IP address. Just roll with it. It's an IP address. All right, and then the stack frame changed event will also have this, and so we will remove this. Oh, I don't want to do that. Yeah, I do want to do that. Again, we're going to take this out. Move that. Safe to remove it here because it's not going to affect the tree. Not part of that tree yet, and now we make this Bex in her. Okay. Okay, so when we get these Bex interpreter events, you go. What do I care about this? Where am I looking at now? I want to look at the debugger. Okay, so when I get these stack frame changed events, I really could do either one, right? Like it's probably cheap to redraw it on every frame. I could just do the interpreter, Bex interpreter, any interpreter. Then I'll say IP is self is EIP, and then self redraw stack. So no matter what event I get, I'm just going to redraw the entire stack frame. And to me, a stack frame is like all the variables that are currently in scope, but in a fourth-like language, there aren't any. You don't really have variables. You have the stack, and then you have the instructions. So like really, what I'm talking about is like the thing that I'm executing. Like that's the main part of the stack frame that I don't know what a better word is for that. The current function, I guess. It's not really a function though. It's the current set of tokens. Anyway, so now if I run this, I would expect to see that same picture, but I would expect that to be highlighted as soon as I run this. Boom. It's not highlighted because I didn't tell it to highlight anything. So now when I say redraw stack frame, collect, is there a collect with index? Collect with index. Okay. And then, so then the way to do that would be to say, stack frame child at an IP if child at if present, because you could be past the end of it. If present, then that child, the GS text shape, will say C GS. We just say background. Color the same color. If you don't say this, you have to say color. First, you have to put it in parens, and then you have to say color from hex string, and then colon, and you need the parens because this has a colon in it, and you've already used the colon here. And you say E. Probably very, very, very light gray. I'm just gonna do it like this. Place background with GS fill color. Fill. I think it's fill or fill color. Okay. Maybe it should be fill. All right, so now I expect that to be highlighted. Again. Did not understand child at. Okay. You can certainly say stack frame child at IP, right? Like if I print this out, only integers. What is IP? It's nil. Okay, so we got a little bug. I think it's because I'm not sending when I use these interpreter events. I think when I send them, I'm not always sending the VexRPN interpreter wherever it references the announcer. Let's browse the references to that. Yeah, so this one doesn't have the IP on it. There we have to put it in. That was the issue. Almost certainly that. And no. Oh, right, because we still don't understand that. But now IP is 1, not nil. And so this just isn't there. So what if we say, I was looking for something to say stack frame child at. You do that. Does that give you an error? What does it do? It gives me an error, out of bounds. How do you ask if a DL element has, so let's just get the stack frame here, and then look at the. Well, no, because we want to go all the way up to like. DL element is what I really care about. Somewhere in here, there's something about children. Make this bugger window as big as possible. So we really want something called child at something for child. Oh, okay. So we could just ask for children. Okay. So stack frame children at IP, and then if present, that should work. Because that's part of the collection protocol, I believe. I believe it is. We can just try it, but we can also click on this. So see at if present, we can right click on this and say browse implementers. And if it's in collection, like, yeah, it looks like this is the comment. Oh, although I don't actually see it in the kernel. Collections in small dictionary. Maybe this isn't. Oh, so if absent maybe is. Which is fine. Yes. I think this is going to work. So let's close this debugger. Close this. And again, now I'm going to expect this. Could be in for surprise, but I think it's as soon as I say this. Does not understand that. What is this? This is BL Children Collection. Subclass of BL Children, which is a collection. So it should be one of these. At if absent is there. Okay, so at if absent should work. That's all I really need to do is I guess that's right. If absent, nil. I can have it return nil and say if not. This is silly. If not nil. Current equals this. Then I bet if someone knows small talk out there, there's a better way to do this. Okay, so if not nil, then do that. Not beautiful, but whatever. All right, one more time. Boom, there we go, highlighted. All right, so now we want to send the step method. Do we have step implement? No, I don't think so. I don't believe we've implemented step yet. Do we have? Okay, so if I just tell it to step from the command line, then it should start stepping through here. So if I say RPN step, then it should move to X1. And then we should it should start drawing stuff on the screen. Again, if I start moving this, it's going to jump around like crazy. But somewhere right about there should be enough to see what's on the screen. And it should step through this. Oh, did not understand push. Oh, because data is not, yeah, I called it an order collection. It's not an order collection, it's a stack. Okay, so anywhere I gotta. I want to browse references. Browse references. Reset. That's these two. These should be stack new. Stack new. Okay. When I move them, I call them ordered collection. We got to start over here. Sketch app. Do this, and then step. Right, so somewhere on the screen there should be some there. Right, so we are now stepping through the program you are seeing up here. And now I believe because we're doing it like in GUI events like this, there's there's time for it to react. It's able to react within the thread, and then it'll actually draw everything in the right place. Yeah, look at that. That's beautiful. Ah, beautiful, beautiful, beautiful. Okay. I'm tempted to rename this word run to load, because maybe input, maybe load is fine. A message to load. Okay. I don't know why you can't do that refactoring, because it won't let you do it, but you can just say load, and then you can save it, right? Right, so now if I open up run, I can just remove this. Yeah, now it's gone, and then we say load. Right? You don't have to make it a refactoring, but the refactoring browser will not let you do that. Okay, so we do want to see scene clear, and then we want to run this, or rather load this. I should put that up there, and then when we step it, boom, 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 boom. It is now making the nice little picture. Okay. I guess potentially I could. I'm fine with this. This is totally fine for me as an input method. At some point, probably there should be a REPL or whatever, but whatever. Who cares? This is a very janky user interface. Like everything about it is weird. Like the way these things size and whatnot. Okay, so I would say the basic interpreter is working for primitives, and now we need to do definition. So okay, so I'm going to go ahead and commit this. Go to Git, pharo, repository in which this resides on GitHub. Yes, for tangent storm -pharo. Commit. Why are all those missing? Oh, because I renamed the class. Right, so Bex, working interpreter, working interpreter for primitives. Yeah, whatever. Working interpreter plus debugger, and debugger, and debugger, friends and debugger for. Okay, and I'll go ahead and push this up to GitHub. Tangent storm pharo. The whole drawing library is in here. It's a little hard to install. You're on your own. You have to basically come here and press all these. Not automated yet. Okay. So now definitions. And as soon as I put something here that says, so again, like again from the previous video, I want to be able to say something like that. So this is a Forth-like language, and in Forth, the colon is traditionally the word you use, or the word you use to introduce a new definition, define a new word. So I'm going to define the word init like this, and it should do these things. So the colon starts the definition, semicolon ends the definition, and then it's defined. Now, if I run this right now, I suspect we'll get this up here. Right? We're going to get a colon up here, and we don't know what to do with that. Hang on. Yeah, I must have had something highlighted. So when I step into this, it's going to fail because it doesn't recognize this symbol, which is as it should be, right? And then it'll tell me where the string is. Okay, so so Forth is normally you make a distinction between like not necessarily a compiled language and an interpreted language, because you could have a compiler or interpreter for the same language, but Forth itself is both a compiler and an interpreter at the same time, and like any particular word can switch. Basically, the colon is the word that turns on the compiler. And so when when the colon is encountered in the input stream, then that how would you say it? The colon causes the execution to stop. So normally Forth is just sitting there like reading input from its buffer, and when there's input in the buffer, it parses a token, executes that token, or handles that token. And what does that mean? Well, it generally looks up the value of that token in a dictionary, and then that dictionary says, well, this is a word that executes immediately, or whatever. And the colon is a word that executes immediately. And what it does is it turns on the compiler. And then the compiler is a different loop that continues to read from the input buffer. And the first thing it does is it reads a token for a new name that it's going to add to the dictionary. And then it keeps reading until it encounters a semicolon, turn off the compiler. And every time it reads a token, it looks up the address of the definition of that word, if it can find it. And it compiles a call to that address. But we don't have, but this is not that advanced. This is not going to be like that. Rather, this is going to be Forth basically is not like a context-free language. Right? This is going to be a maybe even this is probably even a regular language, right? Because we're not going to have like a lot of like nested control flow and stuff like this. There's going to be flat definitions. And some of them can start with this and end with the semicolon. So everything, what I'm getting at is that this should not be here. This should not be, I want this to be pre-processed and stuck in the dictionary. And then all you will see is init, dupe, br0, and so on. So let us figure out how to do that. So when we call load, I'm actually going to load this up, and I'm going to bring up load here. Oh, so actually when you call do token, it actually is a symbol. It's not a symbol. It's not a symbol. It's not a string, it's a symbol. Because I already called a symbol. So basically the colon is not going to be something you can do at runtime in this language. You're not going to be able to do. It's going to be a preprocessor. and so I'm going to say self collect defs. Read defs. Oh, maybe this is the right. So let's just say this. It's really this. Like it's kind of simple, right? Right. So state is going to be. I'm going to say state equals queue. So we're going to queue up instructions. Let's call it stream. Let's make a stream. And then tokens are going to, tokens is, okay, so stream can be a read stream on this, right? I believe this is how you do it. Can you do this? Read stream on. I think that's the right word. Read stream on hello. And then you run this, and then you get a stream. Contents is okay. Oh, I lost my. By looking at the XRP interpreter. Got it right. When was it? If you hit this button, you inspect the class. Rather, this button, you inspect the class, and you have all these different things out here. But if you control B on it, then you just get the that gray bar. You're not inspecting the class. You're just looking at a view of the class. You're looking at the browser. Cool. The coder. Okay, so I want to say, what do I want to say? Lost my train of thought a little bit. Oh, I want to parse these things. So inside of the load method, I did lose the work I was that's okay. I want to say, so let's make a stream. I call it RS, usually RS for read stream. Say read stream RS is equal to read stream on these symbols. Okay. And then state there's going to be a three state system. And the state is going to be state is ready, which is like the initial state. So eval, I guess. State is the eval. It's going to be one of three symbols. So state is going to be eval, define, So new word, eval, new make word, or compile. Right? So we're going to do one of those two things at the time. So do I even need a stream on this? I don't think so. I don't need the stream. We're just going to say one of these things. And then these things, and we're going to say do. And then we're going to say toke. And we're going to say toke, which is the thing, is going to be ordered collection do. And if state equal to eval, then if true, then toke is equal to the colon. Is this a symbol? No. So you have to wrap it in this. Just as a test, as a sanity check, I say as symbol equals this. I think that should be true. Print that, it's true. I could have even done that in line here. Okay, so but if the token is equal to that symbol, if true, then state is equal to make word. We'll just call it colon. Or how about def? Define. Eval, defined, compile. Okay, so if we see that token and we're in the eval state, then we're going to switch over to the define state. If false, then the state, oh no, rather than if false, then we're going to tokes add token. We're going to add the token. Okay, that's this one. State is equal to define if true. I'm gonna change this. I'm gonna say state and states, and then so state actions. I don't want to execute more than one of them. Like here, I'm setting the state to define. I don't want to test whether the state is right after that because it's true, and then I don't want to put a bunch of if, then, and what I'm going to do instead is I'm going to make a dictionary. This could be like its own little like. There's a number of different ways you can handle this dispatch, but I'm just going to make a dictionary. Like it could be, I could be using the methods here, method dictionary itself, and just like run do token and change how do token and put the state on this object itself on the interpreter. But this is just a simple pre-processing step. I know exactly what I want to do here, so I'm just going to do it in line here. So dictionary, new, or even like this. Let's do it like this. Define it this way. So eval is going to be something, some block, right? Our scope and then do something, right? I kind of wish I could close over the variable token, then I didn't have to define it, but it doesn't matter. Define, we're going to do it like this for now. And maybe we'll fix this up later. Compile. So if we want to evaluate a token, then do this. I guess I could do it this way. Make it global here. Token state. Okay, so now we don't need. I like that it's inside of here. Okay, so state actions equals scope, define, compile, and then we're going to call it, say, as dictionary. We'll call it action. Methods even. This is basically object oriented batch here. Okay, so now the state is going to say actions at state, right? So whatever state we're currently in is going to be a block. We're going to get a block back, and then we're going to pass it in the token, and that's what we're going to do. It almost looks like you can remove this, but you can't. Really, you can't just pass this to do because the state is changing. If state were constant, then you could just pass it to do, and then you would need this pattern around it whenever you pass a block to. Okay, so this is going to be the dispatch, and we're done. Okay, this now moves inside of here. So everything I was saying over there is going to move inside of here. So if it's true, then so in eval mode, if the token is a colon, then we move to the defined state. And if false, otherwise, we add the token to the loop. Okay. If we are in define mode, then okay, so we need a buff. Buff is going to be equal to tokes at the start. But we are going to put into buff at every time. Buff add token. So now, when we define something, we are going to make a new thing, and buff is going to be a new ordered collection. Actually, we're going to just say defs. So defs is a dictionary that we already have. Defs at toke. So we're in definition mode. We're in define mode. And now we've moved to the next word. So the colon put us into definition mode. This colon put us in definition mode. Now we're going to look at init and want to take that init token and make that a key in the dictionary. So at that token, we're going to put this new thing, buff equals order collection new. We're going to overwrite that dictionary, and we're going to start writing to that. We're going to create an entry in that dictionary or overwrite the existing entry, and we're going to put a new definition in that spot. And there we go. And then we are immediately going to transfer, after we've taken this one word, we are going to now say state is equal compile. There we go. And now in compiled mode, doing a little bookkeeping here. This probably should be its own little function, or method, but whatever. Stick with it. In compile mode, and really it's just going to be like this. Normally this would be, normally you would write here, instead of adding it into a token, you just execute it, right? You just execute it live. But because we're sticking in the debugger, then you don't execute it live. If we're going to step it, we're always going to step it, right? It's not a language that runs on its own. It's always going to run in step mode. Oh, right. So actually, the difference is that tokes add, right? Okay. We don't need this. Buff can just be nil. And then here, now we're going to add it to token. Otherwise, we'd have to keep it. Push it onto a stack or something. We don't need to do that. There's no nesting, so we don't have to worry about this. There's no. Just the token buffer is where it goes. Okay, so then otherwise, here we're going to add it to the buffer, and we even, instead of a buff, we call it def. That makes more sense. So hang on a second. If the token in compile mode is a semicolon, then the state is going to revert back to eval. If it is not a semicolon, then we're going to add it to the current. We're going to add the current token. That's it. And there's a dictionary for actions. And this is all garbage. Like 1:23 in the morning. But we're almost done. Yep. Good. Action, death, everything's good. I guess my head's in the way. Not much to it. I think this works. I think when we run this again, everything from here to here is stripped out. You won't be able to see the dictionary, but if I can ask for it, so let's add an accessor for that. So defs is going to return defs. then I believe we will see. I think it'll work. When we run this, boom. Oh, it didn't. It didn't include the colon. One moment, please. This is wrong. And this is wrong. They should be assignments. Otherwise, they're just checking for equals. Okay, so this can go away. And now it's. There you go. Okay, but it does not. So now if I say like RPN, I guess if I just browse this, it shows me the definitions, and one of the definitions. Double click on this. One of the definitions is a init, and then the definition of an init is this. So this would be a nice place to put like the dictionary and see what all these methods are, and then like be able to execute them or whatever. And you would have like a this is a good place to put this debugger and all that stuff. But and maybe even a command line over. But I'm not going to worry about that now. That's a wonderful feature of this called a moldable development environment, where you're always adding tools as you go along. But I think this is good. I'm adding my tool here into my application. And eventually this button, this word step is going to be a button right here. And what it would do is dive into this. And so what we need to do to fix this, to make this work, is we need to implement return. Then in doToken, so we need to implement doToken to go into a statement. Okay, so so self, or we just say defs at a symbol if present. We're going to do one thing. If absent, then we're going to go back to just performing the symbol. So if it's present, what will we do? What we will do is we will say control. We're gonna push the current state onto the control stack. The data stack stays the same. So the nice thing about a Forth-like language, in most languages, you have a stack frame that includes the arguments to the current function, or the procedure, or whatever method, whatever it is, whatever you call it in your language, and it's mixed in with the control flow, the IP, the instruction pointer within that function. and the stack contains like when you return, you look at the stack frame and you extract the previous instruction pointer, and so that's how you restore your state, right? And then you just so whatever's in that frame, you just discard it, and then you go back to the old instruction pointer. But in a forth-like language, you have two stacks, so you separate those two things. And because the control is all in the control stack, the return address is always in the control stack. Then you're not polluting the data stack, right? So the data stack can be manipulated, and basically the data stack becomes the argument to everything. So that's what makes it so concise. You don't have to worry about passing arguments because every function takes the same argument. The same argument being the stack. And then you can create variables if you need things, and then you can push them onto the stack or whatever. But it makes it for a very, very simple language. So we're preserving the data stack as we go along. In this case, we haven't really looked at putting things on the data stack all that much. The system already was doing that. The RPN interpreter, the drawing tool was already doing that. But basically, this push thing pushes some piece of data onto the stack, and in practice, it's always a node in our graph that we're drawing. So to keep our hands off of that, we're going to put the control flow in here. So what we do is we push something, and we're going to push an array containing the IP, the current IP address, current instruction pointer, and then we have to know what definition we're looking at. So either so that's what was context. That's it. We're going to push those things. We're going to push the IP, the instruction pointer and the context as an array onto the stack. And then we're going to overwrite those two things. So the context is now going to be present, and I guess this would be the def, right? So the tokens are going to be the def. I believe that this is how this works. And then the context is going to be a symbol. So it'll show you that you're in, so we will know what function we're in, what definition we're in. Right? And then the IP is going to be 1. And then right. Yes. And notice that, so if you want to return early from a function, you just call return. Because so I guess this could be an op. Like, I guess this is a built-in op. Anything that doesn't have any unary method, it can be a function. It can be a primitive here. So why not just make this a primitive? So if we need it, we don't have any conditionals, so there's no reason to do that yet, but we can add some conditionals soon. Okay, so all right, so now right now you implicitly return when you reach the end of the definition. And That's what the semicolon does. So basically, when you reach the semicolon, you return. But we're not going to show the semicolon. So what do? Well, you just do the opposite of this. So you're basically throwing away the context. You don't need this anymore. You don't need this anymore. So what we're going to say is temp, or even just frame, ret, I don't know, return, frame. Frame is a good word. So frame is equal to control top, and then IP is going to be frame first, and context is going to be frame second. And then now context equals self initial context, which is not a thing. Initial CTX. It's this word top. I'm going to make that a function. Just so I'm not duplicating the word, because in case I change it somewhere. And I'm just going to return that symbol. And then I'm going to, when I initialize here, I'm going to use that. Not initialize, reset. I'm going to say self initial. Okay. And then, but I don't actually want to sign this. I want to test for that. Self initial context equals context. Why is it doing that? Oh, I know, because I haven't used it yet. I thought it was an error, but it's not. So if that's true, then so we want to restore the tokens, the list of tokens. Tokes is equal to not tokes. Oh, I'm using this mentally for two things right now. Got two different roles, because it's both the top level stuff and the other. I'm just going to put the top level stuff in the dictionary, and that way this is free to just be whatever it needs to be. Then I don't even need to test for this. I just need to say tokes equals defs at context. And then when I say load here, rather than saying tokes equals order collection new, oh, this is actually fine. And then I will say defs at self initial context put tokes. Because it is both the list of current tokens and the thing you have to return to. So now I'm safe to reassign tokes as I step into a definition, is what this does. Right, so we step into the definition and then we reassign tokes. We assign the instruction pointer to be the first token in that list, point at the first token in that list. And then we need to say self frame changed. Then we're going to create a method for that. And that's going to be wherever we send that announcer. This, do that. Self frame changed. Have something like events. Yeah, events. Okay. All right, so self frame changed. Self perform symbol. Is it already moving? Why is it, what would cause it to move? That causes it. Okay, that's fine. Even the step, so maybe this is redundant. Maybe I don't even need to change it. Whatever. I'm gonna. There's only one thing listening to it, so maybe just anything changed. I think this works. I think if I press this here, okay, now I say step, and I think what I should see is the definition of a init. Go. But because I set it to 1, I gotta set it to 0. Set to 0. Set IP to 0 because we're called from step. From step, which increments it. And that's a little weird, but I've had to do that numerous times. Okay, so boom. There we go. Now x0 should put this back up. Oh, did it? Now we're into dupe. PR0, swap high. Yeah, I would say that is a debugger with definitions. We have functions. We don't have conditionals. The one other thing we need is some kind of conditional. Make a true language. Because with names you can have recursion. And so you need a conditional to break out of the recursion. If you have a sequence, you have mutable state, you have a sequence, you have conditionals, and you have repetition, some kind of repetition. So in this case, recursion. That's everything you need to have a Turing complete language. That's proven many, many years ago. It's called the structured program theorem. Any language can be reduced to an if, to some kind of arithmetic, some modification of the state of the memory, right? Sequences of that, and then a while loop and a if statement, if and while. So a conditional jump, conditional forward jump is if, and then a conditional backward jump, or a backward jump followed by a conditional forward jump is a while statement. So those are the four things you need. You need like mutable state, sequences, conditions, and repetition, and then you have a Turing complete language that can do anything you want to do. This is not such a thing because we don't have a conditional yet. But we have and we're not going to take advantage of the repetition part. But really, this is just like it's a very simple language, but it works. I made a definition. I called it. The next step for me is going to be to break some of these things out uh, into definitions that actually walk the tree. And so then I probably will need some kind of like conditionals. But I'm going to save that for another day. It's not that hard. You just need a forward jump, forward jump, backward jump, and like there's lots of ways to do it. I think at some point I'm going to make a video about like I've got like a real like a very small fourth-like interpreter called B4 that starts from a virtual machine, and then there's an assembler, which is also like a fourth-like assembler. Basically, some of the registers are used as the dictionary. So your dictionary is just like one-letter characters, and you address those registers by their associated characters, and it's got two stacks, and so it's a very tiny fourth-like language, and it's called B4. There's a tangent storm B4 on GitHub. There's an implementation in Free Pascal. There's an implementation in J. Probably at some point there's going to be an implementation in I don't know, probably Godot, and probably this Smalltalk here. And the idea for me is to make this little virtual machine that has a bunch of common utilities that I use everywhere, parsers and all built in, so I don't have to. When I'm learning a new language, I can just take that. My learning exercise for the language can be to build the virtual machine, and then I have all my tools, and I don't, I get at the thing that I wanted the language for. So I use a lot of different languages. But that's a story for another day. But the point of that was that there probably will be, once I make this tool, this animation tool, I'm making it to make presentations, and so this is going to probably help me present things like that in the future better. So it'll be a much more scripted and polished, but in other words, I hope to make a better version of this video that's even shorter. But I think this was like about 2 hours, and the previous one was about 2 hours. I think they were both about an hour and 45 minutes. I think that's pretty good. So within 4 hours, I have a working language here, minus the conditionals, and I think that's pretty cool. The appeal of Forth is that you can just sit down and make something small like this, a dictionary and two stacks, and a list for your instructions, and you have a working interpreter, and that's pretty darn cool as far as I'm concerned. Now you're able to plug in whatever you want, and the idea is I can separate the control flow for like walking this tree from the animations, and then each animation can be primitive. Primitive meaning it's a Smalltalk thing that gets fired off. I don't have to write that in this tiny language. I can write it in Smalltalk, or I can write it as an animation using my animation tools, and give it a name, and then fire it off, and then yeah. But still be able to control that from here, and I think that's neat. I think that's pretty cool. I think it's going to be, well, it's going to be more, you can put this in one string, and I don't know. I took a bet on this. I think it's going to be a good tool to have like a little tiny language in here for making animations. It was fun to make. I like doing this kind of stuff. I like making videos about this kind of stuff. Maybe it was a bit of an over-engineered solution for my current problem, but I think it's going to pay off, so I'm happy with this. And with that, that's enough rambling. So thank you so much for watching. Yeah, I do this often. I have videos of like all kinds of stuff. So check out my channel. Let me know what you think. Ask any questions you have in the comments. And I hope to see you again soon.